Now we look at chapter 19 on electrochemistry. And this chapter has three parts to it. First, we need to review some issues on oxidation reduction. The process by which electrochemistry takes place is through oxidation and reduction reactions. Specifically, we're going to look at the single replacement reactions. And that will lead us to, or into what we call the activity series. Of elements, as well as the reduction potential table that we'll use extensively to evaluate the electrochemical process. Once we've reviewed that, we want to look at electrolysis. And this is the process of driving a chemical reaction using electrical energy. And the electrolysis process in its basically is non-spontaneous. That is delta G being greater than 0 requires the input of energy to drive the reactions. So in electrolytic process, we have electrical energy producing chemical reactions. The second part, or the third part in our chapter, but the second part of electrochemistry is the galvanic process. And here we are dealing primarily with the Voltac cells. Or simply known as your chemical batteries. And in this section, these are spontaneous chemical reactions. In that the delta G is going to be less than 0 for the process that we're going to be looking at. And so if this is spontaneous, we're taking chemical reactions and generating electrical energy in the galvanic process. So we will begin our study of electrochemistry, again reviewing the oxidation reduction reactions. Now, as we begin with the discussion of oxidation reduction, the single replacement reactions are the primary type of reaction used in electrochemistry. Single replacement reactions are defined by an empirical relationship: A plus Bx goes to Ax plus B. In this, a more reactive or active element will replace a less reactive element Okay, and it'll produce an AX plus B. Now, to determine if one element is more reactive than the other, we look at the series of elements called the activity series. And the activity series will be a list of metals, and in the case of halogens also, in order of decreasing activity. Now here is a table we call the activity series, and they're pretty much common. They'll list the most active elements at the top, and the less active elements will be toward the bottom. So anything up at the top here will replace anything below it. So for example, lithium would replace any of the elements below it. Or if we drop down to magnesium as an example, it'll replace aluminum, zinc, chrome on down. But magnesium will not replace lithium, potassium, barium, calcium, and sodium. So we look to this as an indicator of whose will replace whom. Okay, so we come back here and we choose a reaction. Let's take zinc, for example, as a metal in a solution of copper 2 ions, aqueous, and we'll find that the zinc, well, let me write it in compound form. The spectator ion for copper sulfate, for example. Then we have the BX. This will go to the zinc, will in fact replace the copper, zinc, and becomes zinc sulfate, aqueous solution, like that, plus the copper will be converted to basic standard state. So this would be, now, I'll make it a little less. A replaces B, it gives me AX plus B, like that. So as we look at the activity, we see that here is zinc right here, and copper is down here. Now, since zinc is above copper in the activity series, then it will in fact replace copper and make the zinc sulfate, and copper will be reduced to basic standard state. Now, as an oxidation reduction process, we look at zinc being changed to zinc ion, zinc plus 2, whereas copper 2 is changed to its basic standard state by undergoing reduction. So in half reactions, the zinc solid will undergo oxidation by giving up a couple of electrons, and the copper in copper 2, copper ion, will gain a couple of electrons from the zinc to produce the reduced form of copper through, and this is reduction. In an oxidation reduction reaction, two issues certainly have to be accounted for. One, you must have a mass balance, and two, a charge balance. And of course, you're familiar with the balancing of chemical reactions. We have 1 and 1 zinc, copper sulfate, sulfate. So that's not a new issue. But you must also have in an oxidation reduction a balance of charge. That is, the number of electrons that are involved in the oxidation must equal the number of electrons involved in the reduction process. And if we add these two reactions together, we get a net ionic equation. And here we see where zinc as a solid undergoes oxidation to reduce the copper to copper standard state, basic standard state, and then zinc becomes aqueous ion +2. So in the context of electrochemistry, we are going to be looking for combinations of oxidation and reduction reactions to drive either the electrolytic process by applying electrical energy, or we're going to be using oxidation reduction reactions that we can pick from the reduction potential table to design or build or predict the outcome of a galvanic Voltac cell. Before we leave the oxidation reduction idea and concept, I just want to show the reduction potential table as I've mentioned it. As you see, the reactions of ions are shown as reduction reactions producing their reduction products here, and of course each one is associated with a voltage we'll talk about later and when we get to galvanic Voltac cells. But fundamentally this is an activity series in itself, in that elements at the top of this table will undergo oxidation against anything to the lower side of the table. That is, lithium will replace elements below it, and an ease of reduction undergo reduction much easier here, and these undergo well, the ones at the bottom undergo reduction much easier than those at the top. Okay, I want to use some examples here and show you how the activity series is used. Okay, so our first example is aluminum will undergo oxidation in the presence of copper, and copper will undergo reduction to basic standard state. Now, to form the balanced oxidation reduction reaction, we have to first note that the aluminum number of electrons involved is 3 electrons, but copper has only 2. So the way we deal with this is mathematical, in that we'll just simply double the aluminum reaction and triple the copper. So this will give us 2 aluminums, 2 aluminum ions, and then 6 electrons. At the same time, we'll have 3 copper 2 ions, 6 electrons, and 3 reduced 3 moles of the copper. So we then can simply cancel the electrons out and then add the aluminum oxidation reaction to the reduction reaction of copper. So this gives us the net reaction between these two to give 2 aluminums, 2 moles of aluminums, 3 moles of copper, 2 moles of aluminum ions with 3 moles of copper. Now, we'll be using this type of reaction in both the galvanic as well as the electrolytic process. One more example before we leave this topic. the activity series of the halogens follows this order of activity. Chloride, even though it's below fluoride in the group, is more active than fluoride, which is more active than bromide, or more active than iodide. So chloride will replace any of the three in a single replacement reaction. Fluoride will replace bromine or iodide, and bromide will replace iodide. And so we can look at that as okay. So here we'll have iodide ions in aqueous solution from some salt. Will undergo oxidation in the presence of chlorine gas by gaining a couple of electrons and producing chloride ions, and the charges are equal, so we can cancel those out, and we can take Cl2 as a gas, basic standard state, plus 2 iodide ions to yield 2 chloride ions, plus the iodide in its basic standard state, which is solid. So here's a couple of examples you can use to study the use of the activity series in more active replacing the less active, and here is an example with the halogens.